Okay, I think we'll get started, everyone. So, yeah, welcome to this lecture. This is the first lecture on hybrid workflows. So we are moving to a different SciML technique, a whole different topic. Sid, for the last 4 or 5 or so lectures, has been talking about operator learning and extensions of neural operators. And now it's time to move on to another section of the course, which we call hybrid workflows or differentiable physics in general. So that's going to take us over the next 4 lectures or so. It will also include an introduction to JAX, which is a kind of new programming library, which is really interesting and helps do these or code these types of workflows. And then finally, we'll move on to symbolic regression and model discovery as the kind of last lecture. Then I'll do a course summary. And then we have our two guest lectures on machine learning for biology and chemistry. So this is the kind of broad course overview that I showed at the start of the course in the first lecture. So this is just saying what I just said, just in pictures. So yeah, we had introduction to deep learning, and then we did a big section on physics-informed neural networks. Sid has been taking the course over operator learning, and he's also talked about transformers and their applications. And now I'm going to be explaining what a hybrid workflow is, what differentiable physics is, and how neural differential equations relate to those workflows, if you've heard of those types of models. And yeah, I'll finish with something on equation discovery. So how does this lecture look? So I'm first going to start with a recap of the limitations of some of the SciML techniques that you've seen so far, and in particular, physics-informed neural networks and neural operators. And after we've discussed those limitations, hopefully that will motivate why we want to use these hybrid scientific machine learning approaches. I'll go into much more detail about what a hybrid approach is, the different types of them. They can be very simple, they can be very complex. And then at the last part of the lecture, I'll be showing you how auto-differentiation is really the key enabler that allows us to train all of these different SciML models, things like pins, neural operators, and hybrid workflows. And so we'll spend quite a lot of time just learning the basics of auto-differentiation. This will set us up for the next lectures on differentiable physics and hybrid workflows coming up. So yeah, by the end of the lecture, hopefully you'll be able to describe or define what a hybrid workflow is, understand why differentiation is so important in scientific machine learning and how it's used to train hybrid workflows. And yeah, that's it. Okay, so let's recap the 2 kind of big techniques that we've looked at so far. And what I want to do is just talk about their pros and their cons, so their advantages and their disadvantages. So physics-informed neural networks, you've all seen this by now, so I'm going to go very quickly. What we do with a physics-informed neural network is we use a neural network to solve a differential equation. And we do it by just simply saying the neural network is a direct approximation of the true solution of the PDE. And we train it with a loss function where we have 2 terms. One asserts that the boundary conditions are imposed, and the second term is the kind of important term which puts the differential equation into the loss function and says that it should be obeyed everywhere in the domain. And so, as I talked you through pins a while ago now, I've tried to tell you about these advantages and disadvantages, and I've got kind of the broad advantages here, which is generally pins are regarded as mesh-free methods. This means that you don't have to create a mesh to solve the differential equation. The pin gives you a functional approximation to the solution. So this can be very beneficial when it's expensive to create meshes. I think pins best perform on these kind of messy problems where you have some observational data and maybe you want to learn something about the PDE, but you also want to solve the differential equation itself. And also they're mostly unsupervised, so we don't need labeled training data to train pins. They're just, all we need is examples of coordinates in the domain, these co-location points to train them. But as I also showed you in the limitations of pins lectures, there are big limitations of pins, although there are many extensions that are trying to address these and do so sometimes quite successfully. But yeah, a standard pin is often very expensive to train, especially if we just want to carry out a simulation with a pin. It can be really hard to optimize pins. It's not guaranteed by any means that you'll converge on the kind of local minima of this or global minima of this loss function. And pins can be challenging to scale. So we talked about the spectral bias of neural networks and how pins can struggle to solve problems with high frequencies. Okay, now let's swap to operator learning. So this is the subject that Sid's been talking you through over the last chunk of the lectures. So what is operator learning? Well, it's a similar idea. When it's applied to PDEs, operator learning is learning an operator that takes a function to a function. So one interesting task we want to do with PDEs, for example, is to take some either initial condition or maybe some like field of the PDE. So for example, this permeability field in the Darcy PDE. And we want to map it to another function, which is sometimes the solution of the PDE. And Sid talked you through this whole framework that we have of turning continuous functions into discrete functions and how we can approximate this kind of continuous operator with a discrete operator using our different transforms here. So I'm not going to go into this into detail, but here's the loss function that we use when we're training operators is a supervised loss. So we have examples of the PDE solution itself when we train our neural operator here. So yeah, the advantages of operator learning is, once it's been trained, training can be very expensive, but once you've trained your operator, these are often orders of magnitude faster than traditional simulation. It's what we learn is a surrogate model. We can really quickly, given a new permeability field, predict the pressure response. But the limitations, these are still neural networks that are trained in a supervised way, and so we still often need a lot of training data to train neural operators. They can still struggle to generalize. This is still, like I said, a neural network that we're training, and all neural networks can perform worse when they're given inputs that are outside of their training distribution. So if I give this operator like a permeability field that's outside of its training distribution that looks very different, it still may perform much worse. And at a more higher level, when we do these discretization steps where we take the function to its Fourier coefficients so that we can actually do some computation with it, we have to make some assumption about the regularity of the function. Right? We have to choose a finite number of numbers to represent that function, and so there's always some assumption there about the regularity of the functions that you're mapping between. Okay. So let's zoom out even further. Let's just think about deep neural networks in general and actually just ask the question, like, when should we use deep neural networks in our scientific workflows? And I think this is actually quite a nuanced question, and it's not always the case that you should just use a neural network in your workflow because of these kind of limitations of deep neural networks. So we know that, when we train a neural network, it can be really fast, and that can be very beneficial. And neural networks have this amazing property of being able to learn highly nonlinear functions, which again is extremely useful. But we know these limitations by now, and they take a lot of training data. They can be really challenging to optimize. We don't really understand how they process the inputs to their outputs. They can be hard to interpret, and they struggle to generalize. And what I want you to realize in the last two slides is that these limitations still crop up in our scientific machine learning algorithms, right? So even though we're putting scientific understanding into our machine learning algorithm, like either through the loss function or through kind of the architecture of the neural operator, we're still coming up against some of these limitations when we've looked at these methods. So I've got some kind of general advice here. I mean, it doesn't always work. You have to really think about the problem that you want to solve. But this is the kind of general advice that I would give to someone that's considering using deep neural networks in their scientific workflow. And I would say you should use deep neural networks to do these two things, like either to accelerate your workflow. So if you have a workflow that is very, very slow, for example, like a finite element simulation or finite difference simulation, it may be beneficial to use a deep neural network somewhere there to try and speed up that workflow. The other place where you could put a neural network is where you don't understand the part of the workflow. So for example, if you don't understand some of the physics in the model, or if you're not sure exactly how to discretize your model or something like this, learning that discretization or learning that the physics or something like this can be very useful as well. But if you don't have a plan about where you're actually going to use your deep neural network in your workflow, it might not be a good idea to use it. So you really have to think critically about these advantages and these disadvantages. So this leads me on to hybrid SciML workflows. So what is a hybrid scientific machine learning method? Well, it's taking these two ideas where we should just use DNNs to either learn the parts that we're interested in or accelerate our workflow, but maybe not to replace our entire workflow. And so this is the key idea of hybrid SciML algorithms, is to say, instead of throwing away our traditional scientific workflows, these could be things like simulation algorithms or inverse algorithms or denoising algorithms or anything really. What if we put a neural network really tightly inside of that algorithm somewhere instead of replacing it with a neural network? So if you think about pins or operator learning, what we've done so far is just use a neural network to do the whole end-to-end problem. Nowhere have we showed you examples of, say, here's a finite difference scheme and here's a neural network inside of that scheme somewhere. So that's what we're going to be talking about for this lecture and the next few lectures coming up. Does this make sense to everyone as a concept? Yeah, everyone's nodding. Yeah. How about in Zoom? Can you raise your hand in Zoom? Just let me know if you're following. Great. Okay, good. Cool. So yeah, I showed you again in the very first lecture of the course these kind of three broad categories of SciML that I tried to categorize all these different SciML methods into. And I would say we've done a lot on the loss function. We've talked about pins. We've also talked about architectural or kind of clever architectures for science, so for neural operators being examples of that. So now we're going to move on to this final class of algorithms, these hybrid approaches. The final thing to talk about at a high level before we get into the details is we imagine this kind of spectrum of scientific machine learning methods, right? So you have on the left a machine learning method that doesn't have any kind of understanding of scientific understanding. And on the right, you might have one of these traditional methods that doesn't use any machine learning at all. And so now we're talking about these hybrid approaches, which you might consider to be more to the right, where we take a traditional workflow and put machine learning into a very small part of that workflow somehow. Okay, so let's talk about probably the simplest possible hybrid workflow to start with. And then we're going to be talking about more advanced hybrid workflows after this. So the simplest possible workflow is what I would call a residual modeling approach. So what we do is very, very simple. Let's say that we have some physical model. It could be any physical model, which has some inputs X and some outputs Y. This could be a simulation, for example. X could be the initial conditions of the simulation, and Y could be the output of the simulation. And what we're imagining here is the case where, that second case that I described, where we don't maybe understand all of the physics of the model. So maybe there's some unexplained physics that we want to account for, but we don't know, and we don't know how to write inside of this blue box. And so what a residual modeling approach says is, okay, there's some unknown physics or kind of relationship between Y and X that we don't understand. So let's just model that residual relationship with a neural network, and we'll try and learn that relationship from data. So we phrase Y here, our solution, as the physics model plus the neural network. So I've actually just described when this is useful. So this is useful when we have an incomplete understanding of physics, and when another reason is when this physics model is like maybe like full-blown physics model is too expensive to run. So this could be like a more approximate model that's faster, for example. And compared to naive machine learning, this is actually an easier task. So can anyone tell me why a residual modeling is easier than like training just replacing the whole physics model with a neural network? Why would that be an easier task? Yeah.
The kind of residuals that you get are like a smaller class of
the
whole functions that
your
model would train on.
Right. Yeah. Exactly. So if we're doing a simulation, for example, learning that entire simulation, that's a really complicated function mapping X, your initial conditions, to your solution. So if we can just do the majority of that complicated function, and then just maybe the residual of that may be a much more simpler function to learn. So yeah, that's exactly it. Another bullet point here I put is that these residual approaches are often way more interpretable than just having one big black box model that we're training. So we might even be able to look at this network and look at the kind of function that it learns and maybe even interpret some physics from it. We might see that this learns like a nonlinear correction to a linear model, for example, and that might be very interesting. Okay. So how do we train this residual network? So we train it in how we would train a normal neural network, in that we match the outputs of this workflow to some labeled training data. So what we say is, okay, so we've got some examples of X and Y, from some real data set perhaps. And we just match the output of the whole residual workflow, so this Y hat here, to our labeled data with a very simple, say, mean squared error loss function. So now all you can do is just plug in our expression for Y hat here into this loss function and here, and then rearrange it. And what you get is a loss function that just matches the neural network to the residual, which is just the difference between the true data and the Y physics model. So this is just our residual difference. That should be very, very obvious. So that's kind of interesting, because what we've done when we evaluate this loss function is we've actually we haven't factored out the physics model, but what we can do is we can just compute the residual in advance. So if we've got lots of training data, we can just generate all of the physics predictions in advance, and then just use that as a labeled training data set to train the neural network. So that's how we'll get our labeled data to train the network. Does this make sense? Yeah. Okay. So let me give you an example. This is what we're going to do is design a residual modeling method to carry out this task, which is to estimate the force on an aerofoil. So this is obviously a really important design task. We want to design efficient aerofoils, and often we have kind of a few kind of variables that we can play around with. And so in particular, we can just assume for now that we want to design the aerofoil shape, and let's just say that it's specified by n coordinates. So we have these x, y coordinates in the domain. The other thing we can specify is the angle of attack of the wing. And so so the simulation task here is given our aerofoil design and the angle of attack, and also we just assume what Reynolds number is the wing is flying through. Let's try and predict what the force is on the wing. And maybe the inverse task is to say, given our simulation model, can we get the best kind of wing shape that maximizes the force on the wing? So the way that we normally do this is to carry out CFD simulation, or the gold standard would be to run a full-blown Navier-Stokes simulation of the flow over this wing and derive from that the force. The difficulty with that is that these CFD simulations, depending on the kind of resolution that you want to run them at, are incredibly expensive. I don't know if you remember that in the first lecture I showed you that simulation of the flow over an aerofoil, and that was run on a supercomputer and took like millions of core hours to run. So how do we get prediction of the force faster, well, what we can do is use a faster but more approximate model. And there are many kind of simulation models or approximate models that we can use instead of full-blown CFD. So this is one model. I'm not going to talk about it in detail. It's enough to know that this model is just an approximate model for giving us the force over the wing, and it's called the Hess-Smith panel method. So you can look it up if you're interested in that more. But what this paper does down here is design a residual method. So this is a neural network here, which takes in the inputs of those from the Hess-Smith panel method. So this is the prediction of the forces from the panel method. And then it also takes in the aerofoil shape and also the Reynolds number and the angle of attack of the wing. And it combines all these inputs together to then finally produce a prediction of the lift force. So you can see how this is a residual model. We're taking in existing predictions from a physical model, an approximate physical model, and then we're combining it with some learned function that tries to improve the prediction of that physical model, which we're going to train from some training data set. So how do you think we should train this? What data should we use to train? Yeah. So I've written it here. So the way that they train this model is to generate a few examples of high fidelity, like CFD simulation data. And then you're going to try and train the neural network so that that it matches the high fidelity data. So the goal is that after training, we have a model which is not only much faster than the CFD, but is more accurate than this just single approximate model that we have. And they train it with this residual loss function that I just showed you, this very simple mean squared error residual loss. Okay, so here are the results from that paper. And what we're showing here are two graphs. And what we're showing is the prediction of the force as a function of the angle of attack of the wing for one particular aerofoil shape. And the black line here tells you how the force varies using the high fidelity CFD simulation, which we're taking as our ground truth. And then the red line here is the prediction of the trained neural network. What's interesting is the difference between these two graphs here is the first graph is when we train a neural network without any of the physics inputs. So we're just training that black box model that I told you about, where the neural network just gets the aerofoil shape and the physical parameters of the flow as the input, and then it's just trained to predict the force from the CFD simulation. So this is exactly the situation that you described. This function is very hard to compute. It's a very complicated function. And the neural network's accuracy is slightly poorer than if we do the second approach, which is the residual method, which I've been describing, and the accuracy improves somewhat. What I find interesting as well is this orange error bars here. So what this is doing is estimating the uncertainty of the neural network's prediction. So the way that they did this in this work was very simply to train an ensemble of neural networks, and each neural network just had a different random initialization of the weights. And this is just quite an easy way of getting uncertainty predictions from neural networks. It's often done. And so not only was the residual network kind of more accurate in its mean prediction, but the uncertainty estimate from that ensemble of networks was smaller as well. So I think this is really nice evidence that, using a neural network in a residual workflow or a hybrid workflow can improve the accuracy and performance of the model just by incorporating physics, as an input to the network. So can anyone tell me why this isn't exactly the residual model that I showed you up here? So why isn't this exactly the same as this, where I'm taking a physics model and adding the neural network? Oh, how is this slightly different? Yeah.
They're not directly mapping it.
Yeah.
Or giving it as input to present even though you're not before.
Yeah. Yeah. So what we've done here is we've not added the output of the network here with the physics prediction here. We've actually incorporated the physics prediction into the last hidden layer and then fed that into the last hidden layer computation. So what does that do? Why is that maybe helpful? Yeah, exactly. So we're not making an addition is quite a strong assumption that we're going to add something like a correction. Here, it could learn to just do an addition, but it could also learn to do some other, maybe more limited, but non-linear kind of composition of the two. So it just adds a bit more flexibility. So this is another thing you can do with these types of residual models is kind of incorporate it at whatever kind of part of the neural network you want. Okay, so what I just described is the simplest possible hybrid workflow. They get much more complex than this. But I've given you the basic idea, and this is the basic idea to incorporate a neural network or some learnable component into our traditional algorithm. So what we did here was we didn't need to know anything about that physics model. I didn't tell you anything about that Hess-Smith panel method, the approximate CFD model. What we did in that workflow before was just to treat it as a black box. All we needed to train the neural network when we derived its loss function was the outputs of the physics model given the inputs. So now what I'm going to move on to are hybrid methods where we don't just treat it as a black box. What we actually do is we open up our existing workflow and we put a neural network into the middle of that workflow somewhere instead. And what we're going to do is we're going to put that learnable component in the workflow, again, either where the workflow is very slow or where we're unsure of the kind of physics assumptions or how we even code the algorithm, we can replace that with a learnable component. Does that make sense how we're going to extend this? Okay. So to be able to describe like a more sophisticated hybrid workflow, I need to describe to you one of these existing traditional workflows in more detail so that you understand where we're going to put a learnable component into it. And so the workflow that we're going to try and improve is a finite difference solver. And it's a finite difference solver that solves the incompressible Navier-Stokes equations. So here are the incompressible Navier-Stokes equations. And these are all the variables that we have in the equations. And our goal is, like, given some initial condition of the flow, to predict the flow velocity through time and the pressure as well through time. And we have some kind of density and we have some viscosity as well. So describing a finite difference solver, or just generally how to solve the Navier-Stokes equations, is a whole course in itself. So I'm not going to go into detail. What I'm going to do is just give you the highest level possible for you to understand how this hybrid workflow is going to be trained, or how we're going to put machine learning into this algorithm. So one very popular way of solving the Navier-Stokes equations is to use this kind of so-called operator splitting numerical solver. So when we solve PDEs numerically, we have to discretize them. And so the first thing that we do in operator splitting is we discretize this equation in time. So we just replace the flow velocity here with its discrete differences, and rearrange it a little bit. And now the problem is that when we discretize this, we can't just evaluate what u at t+1 is immediately because it depends on the pressure at time +1. So operator splitting uses this kind of nice trick where we define this u star velocity here, which just depends. It's the same expression, but with the pressure at the current time step instead of the next time step. And then when we plug this into the top equation, then we end up with this expression for ut plus 1. And then you can incorporate this divergence criteria in the Navier-Stokes equations here. Plug this into the equations, and what falls out is this expression which only depends on the pressure at time plus 1 and the pressure at time the current time step, and this U star quantity which we can compute from the current time step here. So the U star here only depends on UT and PT. So once we've kind of done that rearranging, then we can discretize again, this time in the spatial coordinates, and that turns these Laplacian operators and divergence operators into their matrix equivalents. And what we end up with is some matrix equation here that tells us what the pressure at time t plus 1 is if we solve that matrix equation based on the current pressure at time t and this U star quantity, which depends on the current time step. So don't worry if that was too fast and you didn't get that. That's fine. All you need to know is kind of the basic algorithmic structure of this solver that I've just described. And so what I've done is just written it down as like a loop here, and I've also written the pseudocode of this kind of how this solver would work in this box here. So to time step and to compute the velocity and the pressure as a function of time, at each time step, we just compute this U star quantity using equation 2. Then we solve this matrix equation at the bottom here for the pressure at time plus 1. And then we compute the velocity at time plus 1 just by plugging all of those quantities back into the first discretized equation. And so how does that look in my pseudocode? So it's basically just a for loop with some complicated computation inside the for loop, where we initialize with some known initial velocity and some initial pressure. And then we're given our density and our viscosity parameter. And then we carry out this time stepping, which at each step does this loop that I've just described. So at a high level, does this make sense, or are there any questions on that? Okay. So if I just take that discretized numerical traditional Navier-Stokes solver, what I can do is just plot you some of the simulations. And what we're doing here is we're plotting the simulation of the flow past a cylinder. So this is like a canonical problem to study in fluid dynamics, and a lot of really interesting dynamics happen past the cylinder. We get turbulence and lots of other interesting things happen. But a big limitation of these numerical methods in general, not just in Navier-Stokes equations, is that the fidelity or the quality of the simulation really strongly depends on the discretization that you used. So what I mean is the fidelity of the simulation, or how accurate it is, really depends on the number of discrete points we use in our mesh when we're solving these equations. So on the left here is a low fidelity simulation where we're only using 32 by 32 by 64 cells in our mesh, in our discretized mesh we're solving these equations over. And what you can see is the prediction of this low fidelity solver is way different to if we used a much bigger mesh. So if we used 128 by 128 by 256 cells. And so this is a really big problem. We want to carry out really accurate simulations, but it really depends on the mesh that we use. And the problem really is this, that if we go to those high fidelity solvers, if we use a much bigger mesh, the time it takes to run the solver grows very, very fast. So the low fidelity solver here, for example, takes like 10 seconds per 100 time steps, whereas the high fidelity takes like over 1,000 seconds per time step. So, this is really not scalable to like billions of mesh cells. This is why we take huge supercomputers to run these big simulations when we're using lots of points. So yeah, the discretization induces errors in the solver. This is unavoidable in some way. But using a finite grid to get over that discretization error is much more computationally expensive. So this is a question we're going to ask is, can we put a machine learning component into this algorithm directly into this finite difference solver to try and improve the accuracy of the low fidelity solver, but maybe to try and keep the speed? So can we create a model that is as accurate as the high fidelity model, but as fast as the low fidelity solver? That's the question that we're going to try and solve. So let me just put this traditional Navier-Stokes solver pseudocode up here on the left. This is the same as I showed before. And what I've done here is just draw this out pictorially. So again, it's just a for loop where the for loop has some functions that we're computing, and also inside of the for loop, it has a matrix solve where we're solving for the pressure at time +1. And so we just think of this as taking our initial flow and then carrying out, many low fidelity steps to get the prediction at t +1, t +2, etc. So my question, and I want you to have a discussion with just your neighbor for maybe 1 or 2 minutes. My question is this: where would you think is a good place to put a learnable component, maybe a neural network, inside of this algorithm somewhere? So there's no wrong answer, by the way. There are many really good answers. So just have a discussion, and then I'll ask for your opinion in a few minutes. Okay, so I saw some discussions happening. So can anyone give me an idea of where you might think about putting a neural network into this somewhere? How could you speed it up? How could you improve the accuracy, maybe? Yeah, please.
Usually in these methods, matrix inversion stuff is very slow because
Yep.
it has to be done by approximation.
Yep.
And maybe just replace that.
Yep. Really good idea. So the slowest part of this algorithm by far is this matrix solve. So yeah, if you have if the simulation has n points in the mesh, that matrix can if it's fully populated, it can be n squared. And that's really not scalable. It takes a huge amount of compute to invert that massive matrix, which is what you essentially have to do. So, I mean, there are a lot of clever matrix solvers, which assume sparsity and all this type of stuff. But yeah, absolutely, this is one place that we can have a neural network that can maybe learn either to do the whole solving of the matrix, or maybe to precondition the solver is another option, or to yeah, there are many ways to learn kind of faster matrix solves. So, yeah, that's a really, really good idea. Any other ideas? I saw you two having a good discussion. What were you talking about?
We were also discussing this matrix. So,
Yeah.
it was a bit about if you have different resolutions, that's kind of what we know from about element stuff,
Yeah.
multi bridge approaches,
yes. Yeah.
and learn or maybe the neural network learn the steps up from the different resolutions.
Yeah, I see what you mean. So you could design a solver which is a multi-scale solver. So this is a solver at one scale at the moment with one assumed discretization. You could maybe have a multi-scale solver. And one idea might be to have the neural network learn the high frequency parts, for example, where they're too expensive to carry out the high frequency solve. So yeah, you can have a low frequency part with a summation of a high frequency part. Maybe. Yeah.
Same as for the timestep. So
yeah. Yes. Yeah. Yeah. Yes. Yes. Yeah, so you're imagining a more approximate model in each time step with a residual correction that we learn in each time step. Yeah, very good. So any more before I move on? Okay, so what you just described is very similar to what I'm going to talk about, actually. So this is one way, and what we've realized just now is there's many different approaches, and they're very interesting to study the differences between all these approaches. But what we're going to do to try and improve the accuracy of the low fidelity solver is to add a residual connection, or a residual correction at each time step. So as a picture, the workflow is going to look like this. We're going to take our initial input. We're going to carry out one low fidelity step, just like normal. But then we know that single low fidelity step has introduced discretization errors because the mesh is two cores. And so what we're going to do is we're going to pass that low fidelity simulation to a neural network. And that neural network is going to try and correct it, or it's going to learn a correction that tries to remove the discretization error from that time step. And our goal is to end up with, still at the same time step, a prediction of the flow which is more accurate and maybe more like what the high fidelity solver would have produced. Then we're at time step 1, then we just repeat this process again. So then we take another low fidelity step, and then we add a residual correction from the same neural network. So we use the same neural network in both steps here. So I've written the kind of pseudo code for how this hybrid Navier-Stokes solver would look. And it's very simple. I've highlighted in the code here the changes to the code. So the only change in the algorithm is this extra line inside the for loop, where we take PT and UT here, which is the prediction, the output of the low fidelity step, and we're just going to pass that through a neural network and add it to itself. So that's doing that residual correction that I just talked about. And we have one other input to the function, which is just the theta values of the network. So these are the parameters of the network, if we're going to write this as a function. How does this look to everyone? Yeah. Everyone understands this? Good. Okay. How about in the chat? Can you raise your hand again? This is an important one to understand. Okay, a few hands. Good. Right, so we understand how we've defined our hybrid workflow, and our hope is that once we've trained this network learns a good correction and makes our low fidelity solver more accurate and more like the high fidelity solver. So the big question now is, how do we train this neural network? And so that's the next kind of discussion that I want you to quickly have with your partner again. Just try and think about how you would actually train this neural network. And to help you, just try to think about what training data we need. So when we normally train neural networks, we have examples of the inputs and outputs. So what are those in this case? And even more precisely, can you think about a loss function that we could use based on that training data? So just have a quick discussion, and then we'll talk about that. Okay, let's carry on. So who can think of, maybe first, what should be the kind of training data that we should use? Or more precisely, what do you think of the like inputs and outputs of the network that we would use? Yeah.
The data one time set of input.
Yeah.
The difference between the high and low fidelity and output.
Yeah.
And because they'll make resolutions, you still have to figure it out something more.
Yeah. Yeah. So that's good. So you're right that we want the output of the network to match the high fidelity solver. That's we're going to use that as our ground truth. So we can have a loss function which matches the output of the network to the high fidelity step. So one way you could do that is, like run a high fidelity solver to generate that with the same initial condition to get your kind of labels. And so your input would be the kind of low fidelity step. So I've got a picture of that basically. So this is option 1, how we train the neural network. So we just think about one time step, and we start with some initial input, so initial condition at time t. And we take 2 steps. We do one, which is a low fidelity step, and one is which is a high fidelity step. The low fidelity step is the input to the neural network. High fidelity step is the label that we use to train the neural network. And so we can then train this neural network. Usually we need lots of examples of different inputs and outputs, right? So we can collect lots of just examples of time steps on lots of different simulations and do a low fidelity step and then a high fidelity step on those example time steps to try and train this neural network. And so the loss function would be exactly this, where we have, the input to the network here is the low fidelity step, which I've got with this L index here. So we say, because this is a residual connection, we say the low fidelity step plus the neural network's correction of that low fidelity step should match the high fidelity step at time +1. And we can just rearrange this very slightly, and we can say the neural network should just match the difference between the high fidelity and the low fidelity step. Yeah.
Having to suppose this maybe like taking high fidelity simulation time t is input.
Yeah.
And then mapping that to like the difference.
Yeah. So you would do a high fidelity. So that's kind of what we're doing. So do you mean like downscaling this before we put it into the network? Is that what you mean? Yeah, I think that's, so what you need to do here is you need to, when we're matching the high fidelity and the low fidelity here, we need to downsample the high fidelity step, which is what you suggested already. So I haven't written that explicitly here, but that is something that needs to be done. Maybe your question is answered by the next slide. So can anyone think of a different way to solve this? Or maybe can anyone see it like a flaw of this approach? Is there anything that could go wrong? First of all, do you understand that the neural network here is just learning the residual between the high fidelity and the low fidelity step? That should be, and what's more, we can pre-compute this in advance. So we can run lots of high fidelity simulations, lots of low fidelity simulations, compute their residual, and then just do the loss function. It's very similar to the first simple residual method that I told you about before. Let me give you, yeah, go on. Yeah. Yeah. So how could you improve the loss function with that then? Yeah. Yeah. So you can, it doesn't have to be T, it could be all T ranges. I tried to put it in the summation here, but I haven't been explicit, but you could take time steps from the whole simulation to do it. Right. So the issue here, yeah, go on, you've got it. Yeah. Yeah.
Then I would have my loss function that would be branching out, let's say,
Yeah.
from the fidelity.
Yeah.
But when I do with a low fidelity solver,
yeah.
I continue to iterate to the output of the low fidelity one.
Yeah.
It's the branch I have left.
Yeah.
So
yeah.
how would the neural network correct that?
Exactly. So what you're talking about here is the limitation which I'm about to describe. So there's a problem here in the when we train the neural network, and the problem is the generalization issue of neural networks. You know, they can perform well for inputs that they've seen in their training data, but as soon as I give it an input that is outside of its training distribution, the accuracy of the neural network's going to start to drop off. And what you see is if you run this hybrid solver and you have this neural network in the middle of it, that neural network is going to perform very well when the solver is in training regime, the simulations that it's in. But as soon as the simulation strays out of that training regime, the accuracy starts to really explode, and the network gives you really poor predictions of the residual. So it's this kind of compounding of error through time as the network unrolls through the algorithm. And you can see this when we use this loss function is the network, you can ask the question, what inputs does the network see during training, right? Because this tells you the types of inputs that it's going to be able to solve when it's used after training. So the only inputs this network sees are these like low fidelity time steps. That's all it sees. What it doesn't see is, you can imagine when we run this algorithm, after like 3 time steps, the low fidelity input has been corrected by the neural network like twice before. And so that's going to be very different, maybe potentially very different to the training data that it's in, which are just pure low fidelity time steps. Does this make sense? How we have this so-called train test distribution shift between how we train it and how we carry out inference. So there's another option for training this, which is doing this. And what we do instead is we unroll our algorithm over multiple time steps to train it, instead of just training it over one time step or a collection of many time steps. So we start with some initial time step here. We carry out again a low fidelity step and a high fidelity step, and we then pass our low fidelity step through the neural network to get our neural network's prediction. But then we don't just match the prediction at the first time step here to the high fidelity simulation. What we do is we just carry on simulating. We do another time step and we do a low fidelity step and then do the neural network correction on top, just as I described before. And again, we do a high fidelity step to match to. And then what we say is we use a different loss function where we say the final output of this whole hybrid algorithm unrolled over many time steps should then equal the high fidelity step at the final time step. Or maybe you could have a loss which says each time step, the output should match the high fidelity step, but we're still unrolling it all the way through and summing all of those time step losses together. So the loss function in this case looks slightly different. What we're saying is the hybrid solver, the output of the entire solver should match the high fidelity simulation. Can you see how this is different to doing like a more, what I would say is more naive method of just matching time steps? What we're doing here is we're unrolling the solver and matching the entire output of the solver to the high fidelity simulation. So then you can think about the types of inputs that the neural network sees during training. And what you see now is this, at this point in the workflow, this neural network sees a corrected low fidelity step. So actually, yeah, it sees this fidelity step, which has been corrected previously. So when we're training this network, the difference now is that it's kind of experienced this kind of distribution shift during its training, and it can be more stable when it's over longer time step predictions. So yeah, this is a better situation. The network learns to correct its previous errors, and it reduces this shift. Yeah.
It's like the first option, like a couple of training
Yeah.
steps, and then this is fine-tuned.
Yeah, absolutely. You can that may be easier or faster to train, perhaps. Yeah. You can also do kind of clever schemes where you just learn you have a loss function which just unrolls the network for like one time step, and then maybe later in training you might enroll to more time steps. Yeah. Any other questions on how we train this approach? Okay. So this sounds good. Sounds like we can train this and learn to correct its previous errors in some way. But there's a kind of challenge here, which is our hybrid solver itself, this whole function that also contains all of our traditional numerical steps, like our matrix solves and our other parts of that pseudocode, are all called inside of this function. You know, we have to do a matrix solve at each of these low fidelity steps. But then when we evaluate the loss function, we need to differentiate this loss function with respect to theta, the parameters of the network, if we're going to do gradient descent on this like end-to-end loss function. So what that means is it requires this hybrid solver to be differentiable. We need to be able to differentiate or backpropagate through this whole workflow to collect gradients of the network's weights with respect to the loss function. So yeah, I mean, how do you think this is possible? I think I just showed you a slide that maybe suggested it is. How do you think we would do this in practice? How would we carry out gradient descent on this loss function? How do we evaluate dl by d theta here, with this being a very complicated function? Okay, so I'll tell you. What's really remarkable is that we can use auto differentiation. So Autodiff is this kind of tool in modern deep learning libraries that you've all been using in all of your practicals so far to train your neural networks. So Autodiff, when we're using it to train neural networks, lets us evaluate the gradient of our loss function with respect to the parameters of the network. And what's really remarkable is Autodiff is more general than just being able to train neural networks. Autodiff is actually a much more general tool that allows us to differentiate through practically any function or any algorithm that we define in these modern deep learning frameworks. So what I mean by that is we can define like some arbitrary function in PyTorch, for example. So this is some PyTorch pseudocode. And all we need to do is just define the forward pass of that function, just like you define the forward pass of your neural network in PyTorch, where the forward pass has some initial inputs, has some outputs, and we just match those outputs of the forward model to some desired outputs, which in this case is the output of the hybrid solver. The output of the high fidelity solver. And then we can just, to get the gradient of this loss function with respect to theta, all we need to do is call torch.autograd.grad to get our gradients. So it's pretty powerful, right? This can be incredibly complicated, whatever this function is. It could be a matrix. This particular example contains like matrix solves, etc. And the modern kind of Autodiff frameworks today are powerful enough to be able to handle these kind of really complex functions that we can define. So let me just compare that to how we would train a neural network so you can see the analogy. This is how PyTorch would train a neural network if I just wrote it in like a functional form, so it's a bit easier to compare. You just define here, now your forward function is just the forward function of the neural network. So X here is the input to the network, theta are the parameters of the network. We do some maybe more simpler computation than the hybrid solver. But at the end of the day, these are two just functions, right? They're just functions of vector inputs and they give you vector outputs. And we would train the network in exactly the same way. We'd require gradients on theta, we'd pass the inputs through this function, then we'd evaluate the loss function, then we do autograd. So hopefully you can see like line for line, this is the same workflow. Any questions on this? This is really important to understand that these two are similar, the same basically. Yeah.
You unroll this over many time steps.
Yeah. Yeah. Yes, possibly. Can you think of analogies in machine learning where that also happens? Yeah, this is the thing that I'm thinking of, or machine learning models that incorporate kind of unrolling. Can you think of any? Yeah, exactly. So like this is really cool. So you can actually interpret this as an RNN from a machine learning perspective. You could think of this as like a hidden state, right? Where we've got some shared parameters of the hidden state and that we're unrolling the RNN over. And the only difference to an RNN is that the kind of the cell functions are not like MLPs. Instead, they're like physics functions, right? But otherwise, it has like an architectural similarity to an RNN. So this is really interesting. We're going to talk about this a lot more when we talk about neural differential equations and kind of the equivalence of differential equation solvers and neural network architectures. There's actually a really deep link there that we're gonna discover. Okay. Any other questions? So yeah, there might be issues with the gradients. Getting back to your question, and we'll talk about that. So let's zoom out. This is the key idea that I want you to take away with, is that auto differentiation allows us to differentiate and learn arbitrary algorithms, like arbitrary functions that have learnable parameters in them, that don't just have to be neural network functions. It can be any function, including like simulation functions or even inverse algorithm functions or denoising functions, like any traditional scientific workflow that we have. So we train neural networks using Autodiff. Autodiff is just exact gradients of arbitrary programs, and so we can use it to differentiate and learn traditional algorithms too. I'm calling these hybrid approaches. They're also known as like differential physics approaches. This is just a general idea that we can use Autodiff to differentiate through our existing physical algorithms. So this is kind of a whole class of, or a whole field of scientific machine learning. It's differentiable physics. So here's the results. What I've been talking about is this paper called Solver in the Loop. It's a really great paper. I recommend you reading it. And they propose this residual hybrid method that I've been describing. And long story short, once you train this on many example high fidelity simulations, you do in fact get a hybrid approach which has a much better accuracy compared to the low fidelity solver, but still keeps the same speed of the low fidelity solver. So this is working really nicely. So can anyone tell me where this seems too good to be true, right? We've got a high fidelity simulation with a very fast runtime. So what are the limitations, or where might this break down? Can anyone think? Yeah.
Probably should be like resolution better.
Yeah. It depends on the resolution. So we can't change the resolution of the simulation. Yeah. Yeah. Any other limitations? Yeah. Absolutely. So the network, when we trained it end to end using differentiate through the whole solver, the network does see its previous corrections and tries to correct for them in later steps, but only to some extent. So if the initial condition changes considerably, then the network is still going to suffer from generalization issues. It's not going to see an input that it's in before in its training. So this is what happens if you actually look at so this is the mean absolute error of the velocity. So this is just the test error, comparing the output of the various solvers to the high fidelity ground truth. And this is as a function of step of the simulation. And so the orange or yellow curve here is the error as it accumulates in the low fidelity solver. You can see it starts with zero error, and then rapidly it starts to explode. And then the different lines here are the different options of training that I just showed you. So option one is where we don't differentiate through the whole solver. We just learn individual time step updates. And option two is where we do end-to-end training. And I think what you can see is all of the methods have accumulation of error. So we can't just learn a method that's perfect 3 times. That's incredibly challenging to do, probably impossible. But the end-to-end training seems to be a little more stable at larger time steps. And I would argue it's because it's seen examples of its previous corrections in its training. Okay. So we've covered this hybrid SciML section of the lecture. So I've told you about residual models. I've told you about the simplest approach, and then we talked about how we can open up the kind of traditional algorithm and insert a neural network more tightly into that algorithm. So I'm going to spend the rest of the lecture, and we'll see how we go. Maybe we'll carry on into the lecture on Friday as well, talking about auto differentiation. So what I've tried to tell you is, or show you, that this is such a powerful tool that it's really important to understand how it works in more detail. So I'm going to explain what Autodiff is in more detail and how it works. So we'll take a break, and then we'll get back to the next section. So yeah, I've been trying to explain to you that auto differentiation is this kind of really incredible tool that we've developed from these modern deep learning libraries. And it really is the key enabler that allows us to train these SciML techniques that we've studied so far. So not only does it allow us to train these hybrid algorithms, you've already been using Autodiff to train all of these other models that you've been studying so far. So, Autodiff allows us to differentiate through these really complicated loss functions when we're training physics-informed neural networks. It lets us get the gradients of our neural networks with respect to its inputs, and then differentiate through those gradients again to get the gradients with respect of the loss function with respect to the weights. We use Autodiff to get gradients of the loss function of neural operators to differentiate through these operators. And then these hybrid algorithms, I'm now showing you that we can use Autodiff to differentiate through our existing traditional numerical algorithms as well. So it's well worth kind of understanding more deeply how Autodiff works, how the machinery behind it works, so that you really fully appreciate and understand how these SciML algorithms work and train. So I'm going to talk about Autodiff as a general concept and how it works. So what I showed you just now is we can think of most or nearly all of our kind of programs or scientific programs as simply functions that are vector functions. So what I mean by that is the input to many of our programs that we write in Python or when we're doing scientific workflows just take inputs that are vectors or matrices or something like this. We can think of a matrix as a vector by just unrolling the matrix and just flattening the matrix. So we can just, in general, think of these functions as having an input vector with some usually quite high dimensional number of elements in. So we just say the input concatenation of all these inputs is X. Then the function does a bunch of really complicated series of primitive operations on this input vector. These operations like multiply, trigonometric functions, divides, powers, etc., etc. And then eventually the function that we're running just outputs some other transform vector y, which maybe has a different dimensionality to X. Maybe it has like m elements instead of n. And so if we were to write this mathematically, it's actually quite simple to write down. We just say that our output is some vector valued function with some vector output. And it's just composed of a series of primitive functions that act on X. Does that make sense? So even though we have like matrix solves here, like if you actually went into that matrix solve algorithm, you would just see that it's a bunch of like linear algebra operations, which are just can be then decomposed into multiplies and sums and maybe divides and things like this. So this could have many, many steps in this composition of the functions, but we can write it in this way. So this should also remind you of a neural network, right? So a neural network is a composition of layer functions. So already you're starting to see the analogies between, each line here could be a layer in a neural network somehow, if you thought of it that way. Okay. So then we ask the question, how do we get gradients? So what we care about in Autodiff is, in general, we want to know the gradients of the output of this function with respect to its inputs. That's a more general question than saying what's the gradient of a loss function with respect to theta. But it's the kind of same idea. How do we get gradients of y with respect to x, where in this case y is a vector and x is a vector? So what we do when we're concerned with these vector functions is we care about evaluating objects like the Jacobian. So everyone, hands up if you understand what the Jacobian is or you've seen it before. Yeah, most people. I just want to double check. So this is just a matrix which just has all the possible combinations of partial derivatives of this vector function. So dy by dx1, dy1 by dx1, dy1 by dxn, etc., etc. And we know from kind of our kind of differentiable algebra, we know how to evaluate the Jacobian or how to get it if this vector value function is just a composition of primitive functions. And all we do is just apply the multivariate chain rule. So, dy by dx here is just the chain rule applied to these vector value functions. So each of these individual contributions to the chain rule is just another matrix, which is, all the elements of F2 against all the elements of F1. So this final matrix here has a shape of n by m if our vector value function takes something from n to n. But each of these individual Jacobians in the middle might have different shapes depending on the number of kind of elements of those intermediate functions in the composition. So is this making sense so far? Yeah. Okay. So what is autodifferentiation? Now that I've given you that mathematical framework, just to say, most programs are vector valued functions, at least scientific programs. So what autodifferentiation allows us to do in general, PyTorch, JAX, TensorFlow, is they allow us to efficiently compute these two quantities. So in particular, the vector Jacobian product and the Jacobian vector product. So if I define y as a function of x in my deep learning library or my Autodiff library, that library will give me an efficient algorithm to compute these two quantities, and I don't need to handwrite what these Jacobians are. The algorithm will just do it automatically for me. This is what Autodiff does. So what is the vector Jacobian product? If I just draw that out as a diagram, you have your Jacobian here of that function that I just told you about, and the vector Jacobian takes a vector of n, times it by the matrix, and gives you an output of vector n, and then the Jacobian vector product is where the vector is the other side of the Jacobian and gives you an output of vector n. Okay, so hopefully simple so far. So here's my question. Why is it useful to evaluate the vector Jacobian product or the Jacobian vector product? Why, can you think of a use case? Why did we design Autodiff libraries to give us these quantities? Yeah. Okay, backprops. Can you be more precise? What is it about backprop? Yeah. 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 So how does that relate to a vector Jacobian product or a Jacobian vector product? Yeah. 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 Okay, so you've got it basically. So let's think about training a neural network. And let's think about the loss function. So what we care about when we're training a neural network is the gradient of our loss function with respect to the weights. That's the quantity that we want Autodiff to compute. So if we think of that as a vector function, it takes a vector as input, which is the weights of the neural network. In this case, the output of the function is a scalar value. So it's a vector to scalar map. So then if I remember, the loss function is composed of, again, lots of complicated other functions inside of the loss function when you compute it. So we can apply the chain rule to this function here to then go one step back in the loss function to decompose it in terms of the gradient of the loss with respect to the network, and then the gradient of the network with respect to the thetas, just using this multivariate chain rule that I said before. And what you immediately see is, because the loss is a scalar value here, it's the Jacobian here, which is the loss with respect to the neural network's outputs, is actually not a matrix. It just collapses into a row. And then this row times by the Jacobian for the neural network with respect to the weights is just a vector matrix product. So this is exactly a vector Jacobian product that we want to compute when we evaluate the gradient of the loss function. Can you see that? Yeah. Okay. So this is it basically. Like every single workflow that I've described, we have a loss function with respect to weights, whether it's a pin, whether it's a standard neural network, whether it's a hybrid workflow. So in every situation that I've described, we want to compute a vector Jacobian product. We want to be able to evaluate what this is. Okay. We'll talk about why we might want to use the other one, the Jacobian vector product, maybe later. So then the question is, how do we evaluate the vector Jacobian product? How does the Autodiff library actually compute this? That's the question that we're going to try and answer now. So we can just decompose the VJP into using the chain rule again, assuming that y as a function of x is just a series of primitive operations. So again, we just have the vector here, and we say it's the chain rule with dfn by dfn minus 1 all the way back down to x. So again, F2, F1 here might just be very simple addition, multiply operations that we're applying inside of our really complicated function. Okay. So let me draw out that kind of this chain rule so that you can see it in terms of the size of the matrices that we're dealing with. And I'm going to go back to just a neural network as our function, just to make it easy for you. And so I'm also just going to be describing backprop by doing this. So we're just going to assume y as a function of x is now just our neural network function, which takes x and gives me some vector output. And it's just composed of two fully connected layers. So we've got the first fully connected layer is just outputs a hidden state, which is g, again a vector. And then the final layer gives the output vector. So then we take the gradient of our loss function with respect to our weights. This is something that we want to evaluate when we do gradient descent. And this can be decomposed using the chain rule to get it with respect to the output of the network, and then the output of the network with respect to the first hidden state, and the hidden state with respect to the weights. And remember, the weights is a matrix, but we could just think of that as a vector if we just flatten that, and you could define the Jacobian like that. Okay, so let me draw that out as like the actual matrices that are involved here, because this is very useful to see it as a drawing. So dl by dw1 is just the same shape as the weights, or has the same number of elements as the weights. So let's just say we have p parameters in our neural network here. And then dl by df is just, again, this is a vector with the same number of outputs as the neural network has. Then we have the hidden state Jacobian. It depends on the number of hidden states and the number of inputs to the number of outputs to the network. And then dg by dw here is this one. So it depends on h, the number of hidden states, and the number of parameters here. So you just write out these size of these matrices here, just assuming that we have, say, 100 inputs. Let me just check. Yeah, sorry. So assuming that we have 100 hidden units, 100 outputs, and 10,000 inputs. So you can imagine, say, if this neural network has like an image as an input. So it's like a fully connected network that's doing like a classification of that image. That input images maybe have like 100 by 100 elements or something. So it might have a lot of elements in the input vector. So we have this chain rule. So then we can just think about evaluating it, right? So evaluating it just means doing a lot of matrix multiplies. We're going to multiply all these matrices on the right-hand side together and get this gradient of the weights as the output. So we can just think about evaluating this chain rule, and there are different ways that you can actually evaluate it. So one way you can do it is going from right to left, and so going from this matrix here, timesing it by this matrix, and then timesing it by this vector. And if you just think about the kind of operations that you'll do 100 by 100 matrix by 100 by 1 million matrix, and that will give you about 100 by 1 million matrix as output. And then the final one is to times this vector by that 100 by 1 million matrix, and you get a 1 by 1 million matrix, which is the gradients of the weights. So the problem with this is that you have a massive matrix multiplier in this when we're evaluating the chain rule here. This is a matrix that has 100 by 1 million elements, which is huge, absolutely huge, and takes a lot of effort to compute. There is another way that you can evaluate this. Instead of going from right to left, you can go from left to right and do it in reverse. And what this allows you to do is to always do like a vector Jacobian product instead of having to do this big matrix multiplier when we went from right to left. So we do this vector matrix here, that gives us a new vector, and then we do another vector matrix here, and that gives us the final weight vector. And so what we've done is we've kind of avoided doing this big matrix multiply here in the first step of the forward mode chain rule. Can you see how the order matters here? When we evaluate the chain rule, this is the point that I'm trying to make. Depending on which way you evaluate these matrix multiplies depends on how much computation you do. It's actually a really important thing to know. Okay, so another thing we can look at is we still have a pretty big matrix multiply here. We have 100 by 1 million element matrix here that we need to do a vector matrix multiply with. So if I actually told you that has like 100 million elements, and that's like 0.5 gigabytes in memory, just to train what is a very simple neural network, just takes an image as input and gives you a class or a couple of classes as output. So this is just not practical. That takes a lot of memory just to store that thing into memory. So there's some more tricks that we can do. So what you can realize is that many of these Jacobians, so these intermediate Jacobians, which tell you what the derivative of these primitive operations are with respect to their inputs, they're often very sparse. So what I mean by that is they have zeros in them in a lot of places. So if I think about dg by dw, so what is this? This is just the hidden output with respect to the weights. If you can actually write down the mathematical expression for the Jacobian because it's a very simple linear operation. So it's it's the gradient with respect to weights of this linear operation here. And if you can go away and check that this is true. It's very trivial to show that this matrix just has x's along the row here, and then that x vector is just repeated across all the rows of the vector, across all the rows of the matrix, and there are zeros elsewhere. So this is basically a very sparse matrix, and we can collapse this down into what is mathematically equivalent, which is just a flattened outer product between the gradient of the loss with respect to g and the input vector x, when we're doing this vector Jacobian product in this step here. So what I'm trying to say is we often don't need to compute explicitly or fully populate these Jacobians when we're doing these vector Jacobian products. Often we can just compute these vector Jacobian products efficiently without needing to fully populate that Jacobian. We can collapse that computation down into something that's much more tractable to compute. I'll give you a simpler example. This is a very primitive operation, say y equals sine x, where x is a vector and y is a vector. Then the Jacobian in this case is just a diagonal matrix with the cos x in the diagonal. So you can, if I took a vector and times that by the Jacobian, it's just a dot product between the vector and the cos of the x. So instead of having to compute like naively n squared operations for this Jacobian, I can do it in n operations if I just exploit the sparsity of the Jacobian. Does this make sense how we can increase the efficiency by cleverly understanding what the structure of the Jacobian is? Yeah. Okay, good. So what we've done is we're going to go from left to right because we know that that's more efficient because we're always doing a vector Jacobian product. But what we've also realized is that we don't have to explicitly populate the Jacobian when we're computing that vector Jacobian product. We can just replace it with the more sparse and efficient version of that product. So now we take that down from like a 1 by 100 times 100 by 1 million multiplied to just the outer product of two vectors. And so this is really what makes Autodiff efficient, is exploiting this sparsity in the Jacobian. And it really is what allows us to train like billion parameter models efficiently. And this is why it's so powerful. To summarize, vector Jacobian product, we just use the chain rule to decompose the function down to its primitive operations. And then when we go from left to right, evaluating the vector Jacobian products and collapsing it down to vectors each time. And each vector Jacobian product, we just only need to define the primitive operation, the forward operation, f, and we don't need to define the whole Jacobian. We just need to define the function that computes the vector Jacobian product, the sparse version of that function. Any questions so far? I realized that was probably quite fast for you, but there was a lot of nodding heads, so it seems like you guys are getting it somewhat. Yeah. Okay. So I talked so far about the vector Jacobian product. The Jacobian vector product can be done in exactly the same way. It's just going from right to left instead. So we have Jacobian vector products instead that we're evaluating, and the same holds true that we only need to define the forward operation of the primitive operation. And we don't need to fully populate the Jacobian. We can just define the efficient version of the Jacobian vector product when we're using Autodiff. Okay. So yeah, go on.
When are we doing the vector product to training ground?
Yeah, so that's a good question. When should we use Jacobian vector products, and when should we use vector Jacobian products? I'm going to talk about this here actually, so we can do that. Yeah. So my question is now this: like, what if we want the full Jacobian? So everything so far I've said we can compute efficiently the vector Jacobian product and the Jacobian vector product. So what if I told you I wanted all of the gradients, all the partial derivatives?
It's gonna get them like reconstructed with Jacobian vector products and Jacobian products.
Exactly. Yeah, that's exactly it. So we can just combine VJPs and JVPs together. If you really want the full Jacobian, you can do something like this, where you say the vector that we're timesing the Jacobian with is just a one-shot vector, or a single one inside of zeros. And we just place that one in the row of the Jacobian that we want. And when we do the product, we can just get the first row of the Jacobian. So what you find is a vector Jacobian product gives you the rows of the Jacobian. Like each product gives you one row. And if you do the Jacobian vector product, then each product will give you a column of the Jacobian. So this maybe answers your question. Usually, if you want to compute the whole Jacobian, if that Jacobian is very wide, maybe it just has one row, then a vector Jacobian product is more efficient because you only have to do it once to get the whole row. Rather than if you did a Jacobian vector product instead, you'd have to do it n times for n numbers of columns that you have in that row. That makes sense.
Looking at a lot of meters and not a lot of outputs.
Yeah, so when we train neural networks, we always use the vector Jacobian product because our loss function is a scalar function with respect to the weights, which is a very wide Jacobian. It's just a single row, so we can get it in one hit of the vector Jacobian product. The reason why you might use a Jacobian vector product is if the Jacobian is a column, and in that case, that's usually when you want the gradients of the inputs of the gradients of the network with respect to its inputs, like x, for example. That Jacobian. Let me think about that. Yeah, that Jacobian is a column Jacobian. Yeah. Yeah. Exactly. Yeah. Yeah. If I go all the way back to the definition of the Jacobian. So just think about this. If I want, let me think about this. Oh, I think I said this wrong. So if you want a column, this gives you all the different elements of Y with respect to one input. So if you had like a neural network that gave you many classes, and you want the derivative of each of those classes with respect to an input, then you would use the Jacobian vector product. But we want the rows normally because we want the output of the network with respect to the parameters which are an input of the parameter. So yeah, I said that wrong. Sorry. Yeah. Okay. So just a few more slides to go. I'll stop it in a couple of minutes if I don't make it. So how does this work in practice? So we just all we do when we're using Autodiff in practice is we just write our forward function in Autodiff. So for example, y as a function of x here would just be a neural network forward function. And what we're doing when we're writing that function is just we're defining all the primitive operations that are composed to create that function. So we define the additions, the multiplications, the activations, etc. And so what libraries like PyTorch or TensorFlow do is they build what's called a directed graph of these operations. So they just lay out all of the inputs to the function and how they connect with each other to produce these hidden states and eventually output your Y value here. So this is done kind of behind the scenes in the AutoGrad when you track your gradients in PyTorch or when you call loss.backwards, this is what's happening. And then for each primitive operation in PyTorch, we need to define, or PyTorch needs to define the forward operation, which is like a summation or a multiplication. And then it also defines for each of those operations the vector Jacobian product and the Jacobian vector product. And in particular, the efficient versions of those. So, if the operation is cos x, then it will define that dot product as the Jacobian vector Jacobian product. And then when we call Autodiff to get the gradients to do either the vector Jacobian product or the Jacobian vector product, it evaluates the chain rule, and it does it just by a message passing through the graphs. So you start with your incoming message or incoming vector here, and then at each node on the graph, it will just evaluate the vector Jacobian product or the Jacobian vector product, and evaluate the chain rule just by using message passing, going backwards or forwards through the graph if it's Jacobian vector products. So does that make sense? So I think we'll stop there because it's past the end of the lecture, and I'll just finish the last couple of slides next lecture. So yeah, thanks very much, and I'll see you next week. Oh, Friday, sorry, see you on Friday.